This is section 16.1, double integrals over rectangular regions. Now that chapter 15 is over, which was all about derivatives and the ways that we can use derivatives, it's not that surprising that the next chapter is all about integrals and how we can use integrals. And then after that, we'll mash it all together and show the big vector calculus theorems at the end of the class. So let's jump into section 16.1. The goals here are first to figure out how to actually integrate functions of two variables. Calc 1 and Calc 2 integrals were all integrals where there was only one variable. And now our functions have inputs of x and y. How do we integrate those? Then there's going to be a certain kind of integral called an iterated integral, which we will then use to find the average value of a function, even when the function has two inputs. So let's go. I want to recall how your picture of an integral should be from Calc 1 and Calc 2. So say that you were trying to use an integral to find an area. Say this area under this graph, y equals f of x. If you were using an integral to try to find this area, what you should do, like the whole idea of calculus, is that you should split it up into infinitely many, infinitely small pieces. And the usual way to do that was to say, let's use little tiny rectangles. If I slice this area into lots and lots of really thin rectangles, then the height of this rectangle and the width of this rectangle are something we can find, and then we can find the area of that rectangle. It's an infinitely small rectangle, so its area will be called dA. Its height is f of x, and its width is dx. So dA is f of x dx, and then to get the area, you add up all the little bits of the area. And that's integral of f of x dx. Now, there's some issues here where, I kind of need to decide what the bounds are for this integral, so maybe it'll be from x equals a to x equals b, and then I'll put those bounds on the integral over here, but I can't put the x bounds on this integral. What's the deal with this? So there are some issues, but this is basically how you should imagine that area is calculated with an integral, is that this is add up all the little bits of area. Okay, so what are we going to do now that we have a function of two variables? Now that our function is z equals f of xy, now instead of our function being represented by a curve, instead the function is represented by a surface that's sitting over the plane. So if we do an integral of this surface, now instead we're going to be calculating the volume under this surface. Okay, so imagine trying to calculate the volume under this surface. Ooh, my straight lines are not real straight. And just like how we picked an interval from a to b before, now we'll pick a box from x equals a to x equals b, and y equals c to y equals d. This box. The box is in the xy plane. Now, how do we find the volume of this, I don't know what this is. What shape this, how to describe the shape. Yeah, I don't know. How to find the volume under this surface and above this box? Well, you cut it up into tiny bits. So the volume is going to be add up all the little bits of volume. Well, what kinds of slices will we get? If you use the same plan would be, well, chop up the base into little tiny boxes. And above any little tiny box, you can go up to the surface, and you'll get a little tiny slice of the volume. So this little tiny slice of the volume is dV. And what is dV? Well, approximately it's the length, or the width times the depth times the height. Okay, well, the height is the easiest for us to see. The height is f of xy. The base, though, is like a little bit of x times a little bit of y. So that's going to be dx dy. Or maybe it's dy dx. It's hard to say. Once you've realized that this is how you should write this, you notice that there's a dx and a dy. So you will actually need to take two integrals to get rid of these differentials. This is called a double integral. So we say we're going to integrate dv, but dv is going to come from two variables, x and y, so it will become a double integral when we actually write it out. What are these bounds? Well, somehow the bounds are going to need to be like a to b and c to d, so we'll need to figure out how to write those in there. In this case, since dx is on the inside, I'll write a to b on the inside because this dx goes with the inner integral, and then the y bounds go from c to d, so the outer bounds are from c to d. So it's like there's kind of like an invisible like grouping here where an integral only makes sense with a differential, so this integral must go with this dx, and the outer integral must go with dy. Let's get those out of here. Okay, now in practice, this little tiny shape, this like dv, it's not, I mean, I can't make an infinitely small shape, so before I actually do that, when I'm introducing integrals, I need to come up with a way to write the integral using a Riemann sum to make sure that it really works. So I'll end up saying like, okay, cut the box in the base into little tiny pieces and pick like a little tiny, like a representative point in the box, and there'll be some technical details. But the takeaway should be, just like you calculated area by doing infinitely many infinitely small rectangles, you can find volume by doing infinitely many infinitely small, like these rectangular prisms. So let's see what it looks like what it looks like when you actually write it out as a Riemann sum. You'll say, okay, I'm going to pick a little tiny box, and I'll say that the point in here is xk star, yk star, and I'll say that this is box k. So you divide up the base into a whole bunch of different little squares, like 1, 2, 3, 4, 5, 6, and whenever you get to box number k, you pick a point inside and you call it xk star, yk star. The star represents us getting the option to choose it. So like it could be anything in that box. Okay, if all the possible partitions of the base make this sum come out the same. So what is this sum? This is delta AK, that's the area of this box. It's not that kind of k, it's a subscript. F of xk star yk star is this height like we used before. We add up all the boxes, and then we let the partition size go to 0. So we make really, really, really small slices on the space. Essentially, this is just the technical way to write it so that we can get the intuition that we wanted, which was to cut it up into infinitely many, infinitely small pieces. So when you do this, the thing you get is the double integral of the function. Now, this issue I've been talking about where like it's hard to decide what bounds to put on here, what we start to do more and more as the class goes on, and like we're almost done with the class, I guess. Are we? No, not really. But I don't know. We're getting into the real like tricky stuff at the end of the class, basically. And as we do that, we'll run into this issue more and more, where like I don't have bounds for A. That doesn't really make sense. So where you would normally put the bounds, instead you describe where you're talking about. And here the region R is the whole box. This picture is becoming a total disaster, but the whole box is called R. So this double integral is defined to be this nice limit. So you make the boxes really, really small. You add up every box's contribution to the volume. The contribution to the volume is the height. Times the base. Will you ever have to actually use this definition? No. What you will need to use is you'll need to use this idea that that the volume comes from adding up lots of little tiny slices, and the slices here are like really tall rectangular prisms. Okay, so what does it actually look like to do a double integral? I've hinted at the final answer up here, where you kind of think of it as an x integral and a y integral, like one inside the other. but that's not always how you think about double integrals. Here's our first example. Let me get off of this like green color. It's a little bit sketchy. The blue was fine. So suppose there's some function f. The question is going to ask us, what's f? And instead of directly telling you, hey, let's integrate something, instead I'll ask you the kind of question that is an integral in like Calc 1 or Calc 2, which is where I give you the derivative of the function and I ask you what the function is. So I say, hey, the x partial derivative of my function is this thing, and the y partial derivative of my function is this thing. What's f? So you go, okay, well, I don't know. I mean, if you tell me the derivative, I can rebuild the function by taking the integral. So whatever f is, f should be the integral of fx. Well, let's see. Fx got its derivative taken with respect to x. So let's take the integral with respect to x. If I integrate this with respect to x, 6x plus 2y dx, then, I don't know, I can integrate it, treat y as a constant. I get 3x squared plus 2xy plus c. Now, the plus c is a little bit tricky here. Because I was treating x as the only variable, this c means this is all the stuff that has no x's in it. That means c might be a function of y. Like c could be a number, but c could also be like y to the 6th. We don't know. All we know is that all the terms that have x's in them are listed here. Okay, so this doesn't really tell us what f is, but maybe we can find it out by also dealing with the y partial derivative. So f should also be the integral of fy when we integrate with respect to y. Okay, now I'll integrate with respect to y, and I get 2xy plus c. And here, y was the variable, so c, it might be a number, it might be a scalar, but it could be a function of x. Combined, these two answers tell us what the function is. They both agree that the terms that have both x and y, that's just 2xy. The first solution tells us, well, 3x squared is definitely in there, and there might be some terms with just y's. The second answer tells us there's no terms with just y's. There might be some terms with just x's. So in fact, there is a 3x squared that's explicitly told to us by the first answer, and it's hinted at by the second answer. But there's no y's on their own, because the first answer says there could be, and the second answer says, sorry, no, there are none. What they all agree on, like what we'll never be able to nail down all at once, is there also a constant that has no x's or y's? So I'll have to write like this. So my function f of xy, it's this function, but it could also be any of the functions that are like this, shifted by any constant, where c is an actual real number. So this is my answer. So in this way, we like integrated, but this wasn't a double integral. When I was given the partial derivatives and I had to rebuild the function from those partial derivatives, I just did a single integral of the one partial derivative and a single integral of the other partial derivative. But I can still do this kind of problem. Okay, let's try a couple more examples of this where we're doing single integrals, but we're just practicing thinking about one of the variables as a constant. So here I'm taking the integral of 3x squared y dx. Check this out. Y does not depend on x, so I'll factor it out of the integral so I don't have to think about it. The same way that you would factor out like 3. I don't want to get 3 out of there actually. It's kind of strange. But any constant you could factor out of the integral. The 3 is actually helpful to me, because the integral of 3x squared dx is x cubed. Okay, once you're done with a definite integral, you put the bounds here next to a bracket or something like this. And when you're doing substitution integrals, you may have trained yourself that like when you were doing a substitution to make sure that you wrote down what this 1 and what this 5 were. That starts to get more important again here because I've got two different variables and like which one do I plug the 1 and the 5 into? The answer is 1 and 5 are x's because they're bounds for an x integral. But just to be more clear, I would recommend that you keep track of what your bounds are by just writing it in with the bounds. Then you're in no trouble. You're going to do y times 5 cubed minus y times 1 cubed. So you end up with 124y. Notice that integrating with respect to x clears out all the x's, but it leaves everything else alone, so the y is still here. Also notice that there's no plus c on this answer. That's because it was a definite integral from 1 to 5. Definite integrals wouldn't have a plus c on them. Okay, let's do a couple more. This one is another integral with respect to x. I'm going to pull out the 3. And then because I'm integrating 1 over x, I don't know, I'll just leave it actually. Because the integral of 1 over x dx is ln x. Now here's where it gets a little bit strange. I'm going to remember that these bounds are x equals 1 and x equals y, but that's pretty strange that there's a variable up here. And the trick is that as long as you're keeping track of what you're plugging into what, you just treat y like a constant for this integral. So this is 3 ln y minus 3 ln 1. ln 1 is 0, so my final answer is 3 ln y. Please notice that when you do when you do a definite integral with respect to x, there's no more x's in your answer. Okay, let's try this one. This is the integral from x to 10 of e to the xy dy. Oh, okay, well my y is up here in the exponent and it's multiplied by something. So this is kind of like you should imagine it's like the integral of e to the 13y. In this case, because it's an integral with respect to y, we're treating the x the same way we would treat the number 13. And I think the easiest way to do that is to let u equal the inside function. Then we'll take the derivative of our substitution. We're hoping to get everything in terms of y, so I'll take the derivative with respect to y, and I get x dy. I don't have x dy in my integral, so the same way that I would deal with any other substitution, I solve for whatever I have and substitute that in. So this equals the integral from x to 10 of, okay, I have e to the u, and then dy is 1 over x du. The way I have this written right now is wrong, and depending on how good you were at substitutions, like how much you practiced substitutions in your Calc 1 and Calc 2 classes, you know that when you do a substitution, the bounds are messed up now. These bounds are y bounds. So you have to either remember that by writing y equals and y equals, or you have to change the bounds. I'll show it both ways, and you get to pick whichever way you want to do it. But when you're doing a substitution, you either have to track what the bounds are, or change the bounds. Okay, let's do this integral. The 1 over x is a constant, so the integral is 1 over x e to the u from y equals x to y equals 10. I need to plug in these y's, so I'll have to turn u back into what it is. This is 1 over x e to the xy from y equals x to y equals 10. And then plug these in for y. So I'll get 1 over x e to the y is 10, so 10x, minus 1 over x, here y is x, so I have e to the x squared. Notice this was a definite integral, so there's no plus c. So this was one way, was like you do the substitution, you keep the bounds how they were, and you just track what they are to remember not to plug them in for u. The other way to do it would be to change the bounds, And you do that by saying, well, I used to have y bounds that went from x to 10, but now I have u bounds. If y is x, then what is u? And the substitution equation tells you if y is x, you can just substitute that in and you get that u is x squared. If y is 10, you plug that in for y and you get that u is 10x. If you go this way, which I strongly recommend for the end of chapter 16, like the end of chapter 16 is very memorable, it has crazy integrals with crazy bounds. All the substitutions go really well if you change the bounds. So if you do this work, where you say, okay, I had y bounds, y was x and y was 10, I want u bounds, and you change it, then the end of chapter 16 will be so much better for you. This path looks like, well, now the integral is from u equals x squared to u equals 10x of e to the u times 1 over x du. And now I get 1 over x e to the u. But these are u bounds now, from u equals x squared to u equals 10x. And then you land right here at the answer. So both ways work. One requires more work up front, like more bookkeeping work up front, but you get the payoff is that you don't have to do all of this weird fiddling around with old substitutions. So I really think you need to do it this way if you have any idea what this is. Okay, what are our observations here? Our observations are after you take a definite integral with respect to x, you have no x's left. And after you get a definite integral with respect to y, you get no y's remaining. The last example, we took an integral with respect to y. There's all x's left. So when you do a definite integral with respect to a variable, that variable is gone. What's that good for? Well, that tells us that this is how we could actually find a numerical value for the volume under this surface. If we want the volume under a surface, well, the volume should be a number, like 13.6. But my function has x's and y's in it. To get rid of all the x's and all the y's using all the bounds, we should do an integral with respect to x, and we should do an integral with respect to y. So what you'll be able to do is you can do it in either order. You can do the integral from a to b dx on the outside, and the integral from c to d with respect to y on the inside. This inner integral integrates out the y's, so the y's will be gone, and this outer integral integrates out the x's, so the x's will be gone, and you'll get a scalar at the end. So v, this volume underneath here, can be done this way, or it can be done the other way, as long as we're careful about the order. Like basically you need to make sure that since a and b are x values, that they are written in a place that corresponds with the x integral. When your base is a rectangular region, which it is in 16.1, you can do the integral in either order your choice. Later in this chapter, it becomes difficult to switch the order of the integrals, and that will be a key skill, is like, how do you switch the order? For now, you switch the order by just writing them in a different order. But either way, this will give us the volume under the curve. So let's do one. So here's example 5. We've got some crazy looking surface. Underneath it is some volume. You should imagine that the volume is made by, like, you take little tiny boxes in the xy plane. You go up as high as the surface goes, and that gives you little tiny rectangular prisms who have a height of the function value and have a base of a little bit of area. So the volume is going to be the integral of this function multiplied by a little bit of area. But the area is going to have two differentials in it, dx dy or dy dx for now. So it's going to be a double integral. Okay, let's try it. So our function is x squared y sine of xy squared. Sure. I need two integrals. And I need to either use dx dy or dy dx here. Either one will equal dA. Later, we'll get more ways to write dA. But for now, we've got, it's either like the width times the height or the height times the width. Does one of them look easier than the other to me? I think one order will work and the other one will not. Well, let's just try one, and if it doesn't work, we'll do it the other way. So I'll write dx dy. The inner integral is dx, so the inner bounds will be the x bounds, which are from 0 to pi. The outer integral is dy, so the outer bounds will be the y bounds, which is from 0 to 1. Then we do the inner operation first. So I'll take this x integral. So I'm going to keep the y integral for later. I'll do it later. For now, I'll do the x integral. Okay, I've got x squared y times, oh, I lost the integral sign, times sine of xy squared. The purpose of doing this step is to notice that we're working on the inside integral first. And now I'm just looking at y as though it's a constant and x as though it's the variable. So what would this integral look like? This integral would be an integral where I have x squared, there's some constant that doesn't matter, x squared sine of some constant times x. So think back to Calc 2, where you've got like, I don't know, let's think of y as like 7. 7x squared sine of 49x. This is an integral, I tried to write a question mark, but it looks like some weird 7. This is the integral we would need to do. Now, I would hope to do it by substitution because there's an inside function, but there's actually two functions multiplied together that have nothing to do with each other. So I would have to do this by parts. I don't want to do it by parts. And this kind of laziness is key in successfully completing these problems. When you have made a choice, like I did here, I chose to do dx dy. When you make a choice and you get a hard problem, you need to remember that you made a choice. It's like you're in a maze and you came to a fork in the road and you went this way, and then you realize that like that way is full of spikes. You don't go, oh, spikes, oh well, life sucks. You like go back and you try the other way. So once I get here, I go like, oh man, I hope that's not the best way. So instead, I'll try it in the other order. Same function. But now I'm thinking of the y first, or the y on the inside, and the x on the outside. My bounds, in this case, they just switch. I'd like to warn you one more time that just switching the order of the integral and just switching the bounds does not work in general. It works for rectangles. And the next section is, I think it's the next section, is all about how that's tricky later. But for a rectangle situation where these are all just scalars, these are all just numbers, you can just switch the bounds. Now I'm looking at x as a constant and y as the variable. So now it's like x is like 7. So now it's like 49y sine of 7y squared. This is way better. This integral can be done by substitution, letting u equal the inside function, because the derivative of u will have a single y. So this integral is so much better. And this kind of thing is key in doing double integrals and triple integrals, is that triple integrals are later. I don't know if I mentioned that. But it's key to doing double or triple integrals is choosing the order. And I don't have any magical way to know the right order. Instead, you need the skill of laziness, the skill of, oh, integration by parts. No. That's the skill. So we'll do this instead. We'll let u equal xy squared. Now we're doing a y integral, so we're thinking of y as the variable. So I'll take the derivative with respect to y. I don't have 2xy dy. I have x squared y dy. So I'll multiply both sides by x. and divide both sides by 2. And the reason to do this is that if I multiply by x and divide by 2, I'll get x squared y dy, and then I can turn x squared y dy into whatever all this stuff is on the left side. Remember, when we make a substitution in Calc 3, it's going to be best if we change the bounds. So y was going from 0 to 1. If y is 0, what's u? I'll plug in 0 for y. When you plug in 0 for y, you get that u is 0. If y is 1, what's u? Well, if y is 1, u equals x. So when we finish the substitution, the outer integral is just not done yet. We're doing that later. The inner integral is now an integral with respect to u. It goes from 0 to x. X squared y dy is x over 2 du. And sine of xy squared is sine u. Now here's the trick. X over 2 does not look like a constant to you, but x is not a variable in this integral. In this integral, y is a variable and x is a constant, so you can factor x over 2 out of this integral. I can't get it all the way out to the outside because this outer integral is an x integral, so I can't get it out of there. But I can factor it out of the part that I'm working on right now. Hopefully I don't run out of space. Okay. Now I have the integral of sine u du. That's minus cosine u. Minus cosine u from 0 to x. Notice that because we changed the bounds, I don't ever have to think about y again. I can just plug in my u's into u because I found what u equals. So minus cosine x minus cosine 0. So that's plus 1. Okay, it looks like we didn't escape integration by parts after all, but I think we were going to have to do 2 integration by parts if we did it the other way, and now we'll only have to do 1. So let's finish this integral. First I'll factor out the half, because a half is a constant even for the x integral. And then I'll get the x distributed in there so that I can do... is it easier to just do the whole thing by parts and treating this end as dv? I want to try it. There's a lot of ways to do integration by parts. My initial reaction was that I should factor out the half, distribute the x, deal with x cosine x separately, but I think maybe it's not that useful to do that. I'll just let this be... Let's get colors. I'll just let this be u and this be dv. Uh-oh. U is taken. I already let something equal u. So I'll let this be v and this be dw. So I'll say let v be x over 2. Then dv is half dx. We're letting dw be minus cosine x plus 1 dx. So w is minus sine x plus x. Then what integration by parts does is integration by parts says that the integral of v dw, which is our volume, is vw minus the integral of w dv. And hopefully this new integral is easier than the previous integral. So let's copy it down. V is x over 2. W is minus cosine x plus 1. Now I have an integral of w minus sine x plus x times dv, and dv is half dx. At this point you should worry slightly. What you should worry about is what happened to the bounds. These bounds were x bounds. Well, all of this stuff still has x's in it, it should also get the x bounds applied. So in particular, this part of integration by parts should be from 0 to pi for x, and this integral should be from 0 to pi. So let's do some of that. For the first one, when I plug in pi, I get pi over 2 times 1 plus 1. So all this is pi. When I plug in 0, I get 0 times some stuff. So I get pi minus 0 for that part. For this integral, here's a half floating here forever, so I'll factor out the half, and then I can take these integrals. It's cosine x plus half x squared, all from 0 to pi. This part, cosine pi is minus 1, cosine 0 is 1, so we're actually going to need to do like a bunch of this. So I'm going to have, I'm out of space. Okay, so I'm going to have pi minus 0 at the start. I'm not writing the minus 0 anymore. Minus, okay, plug in pi. Get minus 1 plus a half pi squared. Minus minus, so plus half cosine 0 is 1. So in total, I'm going to have pi minus a fourth pi squared plus a half plus a half. That's plus 1. And that's the final answer. One thing we should definitely check is since we were finding the volume of a shape, and that shape was all above the xy plane, so finding it with an integral actually finds the volume. We don't get any weird like volume that counts negative. I should make sure that this number is actually positive. To estimate that, I'm just going to like think of pi as 3, just as a quick check to make sure that I got a positive number. So this is like 3 plus 1 is 4. So I have 4 in the positive direction. And in the negative direction, I've got like pi squared is about 9, because pi is about 3. So I've got 4 minus 9 fourths. That's still positive. So I feel good about this answer. Cool. I'm worried because this is not the answer I got when I did this the last time. So let's model good behavior here. And when you have an answer and you've done a million algebra steps to get to it, you should also ask a computer to see if you did the integral correctly. So what are we integrating? I'm not sure Wolfram Alpha knows how to do this integral, but we'll try. Okay, so I typed in all of the function, or all this double integral into Wolfram Alpha, and we'll see what happens. What was my answer? My answer was like, that I just got. It was pi minus a fourth pi squared plus 1. No, this answer is like 1 plus pi squared over 4. Well, that's not good. Okay, let's try to find the mistake. If you do a long calculation and there's a mistake somewhere, and you know this by typing in the question into a calculator and getting an answer that's different from yours, what you can do is something called a binary search, which is where you go to a middle step of your problem and ask the computer what the answer is to the middle step. It will probably either be the original answer to the main question or your answer, and depending on what answer you get from the middle step, you can figure out if your error is in the first half of your work or the second half of your work. So I'll just give it this part next. So I have integral 0 to pi, integral 0 to x, sorry, I'm talking about. So I'm going to give it this now, that's halfway, that's in the middle of my work, and see what answer it comes out to. It's probably either this answer or the right answer. So let's see. So it's going to be x over 2 sine u, and that's du dx. That's still the right answer. So that means that up to here, I'm still good. I didn't do this on purpose. I hope you know that. Okay, so let's go to this step right before the integration by parts, and I'll type that in. So I have integral from 0 to pi of x over 2 times minus cosine x plus 1 dx. That's still the right answer. Okay, so I was correct up to here still. V equals x over 2. Derivative is this. dw is all this stuff. Integral is this. That looks good. So did I plug it in wrong? Oh. No. No. It's supposed to be VW, and I put in V and then whatever this is, which is not W. So let's get a better color here. And fix this. W is minus sine x plus x. So when you plug in pi, you get pi over 2 times pi. So that's pi squared over 2. And when you plug in 0, you get a whole bunch of zeros. Okay, so now I just have a pi squared over 2 here. Is that sufficiently different to give me a really different answer? I still get minus a fourth pi squared. Oh, but I have minus a fourth pi squared plus a half pi squared. So that's plus a fourth pi squared. And then I still have plus a half. So now I have 1 plus a fourth pi squared, which I think is the answer that we got from the computer. Yes. Okay, so probably more valuable than me showing you how to do this problem was me showing you how to troubleshoot this problem. I feel like in a programming class, you get taught how to debug a program, and in a math class, you often don't get to see how to debug a math, like a solution to a really long problem. If you have an external source of answers, then you should use it when you're checking your work at intermediate steps. So, found the error. It was a small error. It wasn't even a calculus error. I just copied down the wrong thing. W is over here. Okay, hopefully you don't feel like that wasted your time. Anyway, we have now been able to find the volume under a surface. Okay, that's like the standard thing that we'll do to find a double integral. The other thing we can like easily do is once you know the volume of under a surface, you can find the average height of the surface. In Calc 1, we had the average value of a function was the area under that function. So it would be like you've got some function here. So you take the area under the function and divide it by the width. In this way, area divided by width equals height, well, average height. So we'll do the same thing. We'll say that the average value of our function of two variables is, well, find the volume under the surface. The fraction's going to get really ugly, so I think probably a better way to write it is this way. Find the volume and divide by the area. I don't really know how to write this. I want the area of R. In my notes, did I write it a different way? Oh, I wrote it out. Area of R. That's maybe better. So you want the average height of something, you take the volume or area under it, and divide by the base, the size of the base. It gives you the average height. Okay, why would we ever do this? Well, in this problem, we're talking about a piece of wire which has like an x component to it. So, and it has temperatures at different points on the wire. So x here is a length measurement. But then we're also letting the wire like progress through time. So it has a time element. The temperature of the wire depends on what spot you're looking at on the wire and how much time has elapsed. So the function, the temperature function, is a function of two variables, the location and the time. You'll look into stuff like this if you do a differential equations class. You get to do really awesome problems. I guess it depends what kind of differential equations class it is. But if you don't get it in your first differential equations class, you would get it in some electrical or computer engineering class. It's something called Fourier series. Lets you find these solutions, and they're super awesome. But anyway, let's just look at this problem. So we've got a carbon wire. Its length is pi centimeters. That matters because we're going to be taking a double integral. And so this tells us the bounds on the x variable. It has a thermal diffusivity of 7 square centimeters per second, which we are in no circumstance to figure out what that has to do with anything. But in differential equations class, you would know what that does. Then you stick both ends of the wire in 0 degrees Celsius. So you stick them both in ice, and you heat up the wire in some crazy way to start. So here's t equals 0. At t equals 0, the temperature function for this wire is the left end is stuck in ice. It's colder than ice for a while, and then there's this like hot spot, and then there's another cold spot, and then there's a hot spot, and then there's a cold spot, and then this other end is stuck in ice. What happens when you have a wire that has like different temperatures at different points is that the temperatures equalize over time, and it turns out that the solution looks like this. Now this looks really complicated, but what happens is given any particular point on the wire, if it was a hot point, like this one, it cools off through time. Or if it was a cold point, it warms up through time. And that's all in this solution. Anyway, it has high thermal diffusivity. I guess 7 is high. I don't really know. Let's find the average temperature. Now, the average temperature of the wire is a little bit complicated because the wire's temperature varies based on both space and time. But that's no problem for us anymore. If you need an average value of a function that has two variables, whatever, just use the formula with the double integral over both x and t. So we're going to divide by the area of R. This integral is going to be over this area, whatever this is. Of our function. Notice that this dA is pretty sketchy here because the units of dA are centimeter seconds, because x is centimeters and t is seconds. So the area is also measured in centimeter seconds, but the math doesn't really care about that. It just doesn't matter. We're going from, what are our bounds? I think x goes from 0 to pi. Yeah, and t goes from 0 to 0.1. So I've got pi centimeters times 0.1 seconds. That's the area. And then I'm going to integrate. For now, I don't know what order I'm going to use. But I integrate this crazy function. And this is the real actual solution. This isn't like a crazy made-up function just to be difficult. We're going to integrate this function with respect to x and t. For now, I don't know, I said x first and then t, so we'll try x on the inside and t on the outside. If it goes poorly, we'll switch it. The x bounds were from 0 to pi. The t bounds were from 0 to 0.1. So let's do it. I'm going to have 10 over pi, oh dear, centimeter seconds are in the denominator. The outer integral I'll put off until later. The inner integral I can just do right now. So I'll take the integral with respect to x of this function. All these things with no x's in them are constants. Integral of sine 2x is minus 1/2 cosine of 2x. The second term has a big constant, and we have the integral of sine 5x. That's minus 1/5 cosine of 5x. This is an x integral. Here's our x bounds. They're from 0 to pi. This outer integral we're putting off to later. Now I need to plug in pi and plug in 0. Well, cosine of 2 pi is 1. Cosine of 5 pi is minus 1. Then I plug in 0. Cosine 0 is 1, so I'm going to do minus 3/2 e to the minus 28t. Uh-oh, wait, hang on. So I had minus... Oh, I can't do it in my head. So here's when we plugged in pi. I can't tell if there's 2 or 3 minuses. So here's plugging in pi, and then I'll subtract plugging in 0. When I plug in 0, I get minus 3/2 e to the minus 28t. When I plug in 0 here, I have plus 6/5 e to the minus 175t. Okay, does any of this cancel? Yes, minus 3/2 plus 3/2. So this part cancels. Minus 6/5 minus 6/5, that doesn't cancel. So I have 10 over pi, integral from 0 to 0.1, and I'll have minus 12/5 e to the minus 175t. Notice that when we finished the x integral and you breathe a sigh of relief that the inner integral is done, the x's should be gone. Our goal is to get down to a scalar, like some number of degrees. And so like the x's should be gone at one step and the t's should be gone at the next step. Now, oh crap, I forgot to keep track of the units here. The dx had, the dx was our source of centimeters. So the centimeters have now canceled. The dt, well, the dt is going to be our source of seconds. So at the end, we'll have whatever our function was, which was temperature. Anyway, let's finish this integral. 10 over pi. The integral of an exponential is itself divided by the derivative of the inside here. So I'm going to have 5 times minus 175 e to the minus 175t. From 0 to 0.1. And now I see that I'm going to be plugging ridiculous numbers into crazy exponentials, so I no longer can, it's no longer reasonable to try to get an exact answer here. I guess I can at least get that far and maybe cancel some stuff to make it a little bit easier. But it's going to be 24 over pi, 24 over 175 pi times e to the negative 17.5 minus e to the 0. So this is our final answer. In this situation, because it's a physical example and because this is ridiculous and completely non-understandable, I think I'm going to get a numerical approximation for it. So I got minus 0.04 degrees Celsius. So this is our average temperature over the length of the wire and over time. And the fact that there were 2 variables there and that one was space and one was time just kind of didn't matter to our formula. So hopefully you can see the power of double integrals. Coming up next, we'll deal with how to do double integrals when the base of your shape is not a box, and it'll be a little more tricky. But you should practice these first because there's a lot of worrying about which variable is a constant and which one isn't, and you need to get expert at that first. That's 16.1.